Before being able to correct an error, we must deeply understand it. We must quantify it, understand its causes, and how it evolves over time so that we can adopt the best strategies to solve it. In this lesson, we will undergo a very important paradigm shift. We will no longer assume that we can solve the localization problem perfectly with extreme certainty, so we no longer assume that we will be able to know exactly the coordinates of the robot. Instead, we will switch to a probabilistic approach. We will admit to having only an uncertain estimate of the robot's position affected by measurement errors that makes it impossible to know the exact robot position. As the robot position is uncertain, we will treat it as a random variable for which we can define a probability distribution and therefore a function that indicates not the exact position of the robot, but the most likely ones. The goal of this paradigm shift is to quantify and model the uncertainty affecting the robot's motion and how this uncertainty changes, how it evolves and grows as the robot moves due to the odometry error that accumulate over time. Engineers and mathematicians have an elegant way of solving this type of problems. Create a mathematical model, a system of equations that describes the behavior of the system in order to predict its output based on certain inputs. In this lesson, we will see a mathematical model to describe the odometry motion model of our robot through a system of equations. This model was first proposed in the book Probabilistic Robotics, and to this day, multiple localization algorithms are still using it to describe the motion model of a robot and how it is affected by inevitable measurement errors. To understand how this model works, let's start with its interface, namely with the inputs it receives and the output it provides. As input, the system receives the robot's odometry, so the estimated position and the orientation of the robot coming from the odometry system, whether it's wheel-based odometry system or it's laser odometry or even some more advanced sensor fusion to calculate the odometry of the robot. Odometry, being a cyclical algorithm that constantly measures the variation between the robot's current position and the previous one, provides us with two readings, so with two pose estimates that we can call xt, so the position of the robot at time t, and xt minus 1, so the position of the robot at the previous moment in time, that is the time t minus 1. Their combination represents the robot's odometry calculated as the variation between the current pose and the previous one. However, these two quantities, so xt and xt minus 1, do not represent the true pose of the robot. They represent only an estimate that is calculated by the odometry system. As we already know, this estimate is affected by random errors, such as water on the floor or very long corridors, and so on. Therefore, xt and xt minus 1 are random variables, meaning they can take different values depending on the random events that have occurred. Thus, this model is affected by noise, influencing the calculation of our odometry system and causing it to make mistakes. The goal of this model, therefore, is to take the input, namely the odometry, take into account the noise that inevitably affects the robot's motion, and produce a new estimate of the robot position as a random variable with a certain probability distribution.